So, being that this is the realm of mathematicians, right? Because we're thinking of all of this stuff, which is all maths. What kind of mathematical knowledge could be used to solve this problem? Because this is a big problem, and there's billions, trillions of dollars every year that rides on solving this problem. And it has been solved. Okay, so I'm going to show you one of the most ingenious solutions to it. It's not the only one, it's not unique, but it'll bend your brain a little bit, okay? I know it bent my brain a little bit when I learned it. This is symmetric cryptography, right? What do you think it would be called if the cryptography was not symmetrical in nature? Asymmetric cryptography. So, new little subheading. Asymmetric cryptography. Okay. Here's the picture, right? Here, both people have the same key, basically, okay? But this is thinking about, well, what if, right? The encryption and the decryption processes, right? Were actually if you know how it was encrypted, in this case, you know how to decrypt it, you know how to decipher it. But what if there was a way to encrypt messages and know how it was encrypted, but then not be able to decipher it? What if this was not symmetrical like so? So in order to help you understand, let me give you a picture, which is an alternative to this, okay? I've still got person A. Here we go. Person A in the middle, okay? But I'm going to change it up a little bit. Suppose person A doesn't just want to communicate with one person, right? Wants to communicate with, say, 29 people, okay? So what I want, let's change this now. This is me. What I want is to be able to communicate with all 29 of you, okay? And for you to be able to send messages to me securely, okay? Now let's just think about how I would do this under this model, okay? If I want to send messages to everyone and only I want to receive messages from you guys and only I can read them, okay? Well, one solution would be I get 29 sets of one-time pads, okay? And I give all of you one, and I keep all 29. I have to keep all 29, right? And then every time I get a message from, okay, here's one from Tarush, I go and look through my pile. I'm like, here's Tarush's one-time pad, and then I decipher using that, okay? And then I get a message from Annabelle, and I'm like, okay, this is Annabelle's one, and I look it up, and so on. That's awful. Not just for the fact that I need 29 one-time pads, right? It's confusing. So here's my alternative. Here's all of you guys out here on the side, okay? I don't have the time to draw 29 of you, so I'll just draw 4 of you. Okay. Instead of handing out one-time pads, okay, my keys, as it were, what I do is I hand to all of you guys, everyone, the same thing. I hand you all not keys, but locks. Okay. So here are my little padlocks. Okay. Now just think about this, right? Think about how clever this is, right? Because mathematically this is ingenious, right? If I give you all the same lock, okay, what happens is you compose your message, right? You put it in a box and you slap the lock on, okay? Now, you can't read the message, but you don't need to read the message. It's not for you. You know what was in it anyway because you wrote it, right? The only person who can open the message now is the person with the key, namely me, right? So I've got one key, and it unlocks all of your messages. And as soon as you slap the lock on, no one else can read it except for me, okay? No, even if you've got the lock, right? You can have the lock, but not be able to open it. Does that make sense? You can close the padlock and you're like, oh crap, it's stuck, right? And I need the person with the key to open this up for me. Question?
Doesn't someone else with the same lock then have the same information? Like two people with the same lock can make the same message set?
Okay, all right, so let's come back to this, right? So this idea that you are now in possession of this lock, okay? What power does that give you, okay? Well, yes, I suppose you could both lock up a message in the same way, but then what are you going to do with that message once you have it?
But won't you have an identical message?
Well, but the whole point is that, for instance, okay, so let's push on that. So here's Nikita, right? And you want to send a message to me, okay? And so here's your message, right? Here it is. And you put a lock on it, okay? Now, then this person down here, who looks pretty shifty here? Yeah. Let's make it Tarush. Okay. Tarush wants to know what's in this message. Okay. Now the scenario you were talking about is if he had the exact same message, right, and locked it up in the exact same way. Okay, which is the same. All the locks are identical. Okay. If you guys then send those to me, then yes, the messages would be identical. Okay, and they'd be using the same lock, and I would decrypt them with my key, and they would, sure enough, come up exactly the same. If you said hello, and if you said hello. Okay.
Then we would both know what we were.
Well, that's right, but that was on the assumption that he actually knew your original message in the first place, right? So if he comes to your message secondhand and he didn't know what you sent, he would need my key to open it up, right? So everyone having the locks is no compromise on my security, okay? This is the whole point, that a lock doesn't give you the same information as a key, unlike here, right? Unless, of course, you're a locksmith anyway. Okay, so the point is, though, I'm giving out locks. It's a fundamentally different idea. It's not symmetrical, okay? Now, this is the sort of the analogy, right? But how does this work mathematically? Because, you know, have you ever played that game? Have you ever had someone say, okay, everyone, think of a number. Think of a number, okay? And then they tell you something like, okay, now multiply it by 5, and subtract 1, then take the last digit and add them all up, or something like that, right? And then magically at the end I say, now, is your number 7, right? And you're like, oh, well, how did you do that, right? Now, here's the thing. If you write all that down, it's like symmetric encryption. You can work out exactly what's happened, and you can work out how I did the trick if you write it down, okay? But here, there's this idea that I can give you some kind of mathematical lock, that even when you have the lock, you still can't work it out. With all the time in the world, you won't be able to work it out. So the question is, how does that work, right? Well, I'm going to give you an example, okay?